So let me read the first problem. This one tells that a cylindrical can of length capital L and radius capital R is made of sheet metal of density rho and thickness T, where T is much less than capital R, the radius of this cylindrical can. It is floated in a liquid of density rho F, F for fluid, with the end faces vertical. See this part carefully, slightly unusual way of floating with the end faces vertical. Find an expression for the fraction of the volume submerged. Evaluate your answer for L is equal to 0.60 meter, capital R 0.12 meter, T 2.5 millimeter, density rho of sheet metal 3.1 into 10 to the power 3 kg per meter cube, and density of the liquid rho F is equal to 880 kg per meter cube. So this is the question, and first of all we shall take down the information given here for the cylindrical can that I might show with a figure. This is the can whose length is equal to capital L. There is no need to take down the data now because all data in the last line. At the end, when I put the numerical values, you can straight refer to the question and take down the information here. So length of this can is capital L, and for a circular cross section, radius is capital R. Therefore, diameter that I am showing on my figure, this is 2R. It is further given that the sheet metal has got a thickness very small, that is small t, but it is not like a one-dimensional line. It has got a little bit of thickness because sheet metal means a metal that is made into a sheet, a plate or lamina of a given small thickness, and that thickness is given to be small t, which is much less than the radius of the cylindrical can. So three parameters here: length capital L, radius capital R, and thickness of the sheet metal is small t. And inside this can that is taken to be enclosed, both the sides, this is closed here, so inside it's empty. It's a hollow cylinder in which there is only air trapped. So if nothing is mentioned, we'll ignore the density of air and assume that the space inside the cylinder is completely empty. The metal is only distributed along this lateral surface and on the end faces of the cylindrical can. We are further given symbolically density of the sheet metal is rho, density of the liquid is rho F, and it's understood that rho is greater than rho F. So let me draw the figure next on how this can is floating on the surface of this liquid, and this is my figure, say. Since it is floating with the end faces vertical, it means that the circular faces remain upright like this, and lateral surface of this cylindrical can, that is a two-dimensional, looks like horizontal lines. These lines are parallel to the free surface of the liquid. So condition of flotation, this is the center of gravity of the entire cylindrical can located on the axis of symmetry, and to this point the force of gravity is acting downwards. We call that force as Fg. And center of buoyancy is the point, that is center of gravity of the displaced liquid. Since this part of this cylinder is taken to be immersed, that is also the location of the displaced liquid before displacement. So for that displaced liquid, center of gravity is somewhere a little below than the CG of the entire can, and therefore center of buoyancy also this point through which the buoyant force is acting vertically upwards. Symbolically, this force is called Fb. So of course, if this cylinder is in floating condition, it means the net force acting on it is 0, and we can write down that condition of flotation is Fg is equal to Fb. Now, how to find out this Fg and Fb in terms of the given parameters? We shall assume here that the volume, a little bit of rearrangement with my drawings here to avail some space for writing, and we shall assume now the total volume of this cylindrical can is equal to capital V. So, if the fraction of the volume immersed under the liquid, that is small f, the required quantity in this problem, in that case, the immersed volume can be expressed as V dash is equal to the fraction f multiplied by the whole volume capital V. But what about capital V? Looking at my figure, a cylinder of length L, cross-sectional radius capital R, using the formula of mensuration, this V is equal to pi into R square into L. Therefore, the volume immersed.
Hello students, you got a glimpse of our video lessons through this small lecture. We have hundreds of lectures like this one covering various topics of advanced school level and intermediate physics in our website. They are exhaustive and often accompanied by elaborate diagrams to make concepts even clearer. They are taught with passion and sometimes with a bit of fun. So, at the end of the lesson, you have a commanding grip on the subject and you are ready for the board and competitive exams. Subscribe at physicsacademyonline.com to access video lectures of highest standard on various topics of physics.